Students, in this lecture, I'll be taking the last part of Module 1, that is Stop and Wait Protocol. Okay, so this is a second protocol that is called as Stop and Wait Protocol. This uses both flow and error control. Okay, in this protocol, the sender sends one frame at a time, and after sending one frame at a time, waits for an acknowledgement before sending the next one. Okay, then in order to detect the corrected frames, we need to add a CRC to each data frame. When a frame arrives at the receiver side, it is checked. Then if that CRC is incorrect, or if its CRC is incorrect, the frame is corrupted and silently discarded. The silence of the receiver means that it is a signal for the sender that a frame was either corrupted or lost. Then the sender sends a frame. After sending a frame, every time it starts a timer. So a timer is started every time when the sender sends a frame. Then if an acknowledgement is going to appear or occur or arrive before the timer expires, the timer is stopped and the sender sends the next frame. So the sender will send the next frame when an acknowledgement arrives before the timer expires, the timer is stopped. Okay, now if the timer expires and acknowledgement has not been received, then the sender resends the previous frame, assuming that the frame was either lost or corrupted. So what does this mean is that the sender needs to keep a copy of the frame until its acknowledgement arrives. Until its acknowledgement arrives. When the corresponding acknowledgement arrives, the sender can discard the copy and send the next frame if it is ready. So this is a diagram that is showing the outline of stop and wait protocol. We can see that only one frame and only one acknowledgement can be in the channels at any time. So you can see there is only one frame and only one acknowledgement in the channel at any time. Okay, so you can see sending node, receiving node, then only one frame, acknowledgement at a time. Okay, so next we'll see the, and here the timer has been shown. Okay, then so next we'll see about finite state machines for the primitive stop and wait protocol. So this is a diagram that is going to show the finite state machine for the stop and wait protocol. Okay, so here the sender and receiver states will be described. First we'll talk about sender states. Always a sender is initially in the ready state, but it can move between the ready and blocking state. So is it clear? The sender is initially in the ready state, but it can move between the ready and blocking state. Next we'll see about ready state. When the sender is in this state, it is only waiting for a packet from the network layer. Ready state, when the sender is in this state, it is only waiting for a packet from the network layer. If a packet comes from the network layer, the sender creates a frame, saves a copy of the frame, starts the only timer and sends the frame. The sender then moves to the blocking state. Okay, this is about ready state at sender states. Okay, next we'll see about blocking state. If the sender is in this state, or when the sender is in this state, three events can occur. The first is, if a timeout occurs, the sender resends the saved copy of the frame and restarts the timer. The second is, if a corrupted acknowledgement arrives, it is discarded. C. If an error-free ACK arrives, the sender stops the timer and discards the saved copy of the frame. It then moves to the ready state. Next we'll say about receiver. The receiver is always in the ready state. Two events may occur. One, if an error-free frame arrives, the message in the frame is delivered to the network layer and an ACK is sent. Second is, if a corrupted frame arrives, the frame is discarded. So there is an example that is going to show that the first frame is sent and acknowledgement. You can see the first frame is sent, acknowledgement has been received. The second frame, you can see the second frame is sent, but it is lost. Okay, so after timeout, again the frame is resent. So after timeout, it is resent. Again, you can see third frame is sent, but acknowledgement is lost. Acknowledgement is lost. Okay, so third frame is sent. You can see third frame is sent, acknowledgement is lost. Okay, acknowledgement is lost. Then the frame is again resent. You can see the frame is resent, acknowledgement when it is lost, again it is resent, acknowledged. So, but there is a problem with this scheme. The network layer at the receiver side receives two copies of the third packet. So this is one third packet, again third packet is received, two copies of third packet, which is not right. So we how to correct this problem using sequence number and acknowledgement number will now be discussed. Okay, so we'll see about sequence number and acknowledgement numbers. Whatever example just now we discussed, that needs to be addressed and corrected the problem. Duplicate packets as much as corrupted packets need to be avoided. Okay, so this example where we are going to assume that we are ordering some items online. Assume we are ordering some item online. If each packet defines the specification of an item to be ordered, so if how many packets are there, if each packet defines the specification of item to be ordered, duplicate packets means ordering an item more than once. So duplicate packet means ordering an item more than once. How to correct this problem is we need to add sequence number to the data frames and acknowledgement numbers to the acknowledgement frames. However, numbering in this case is very simple. You can see sequence number always starts with 010101. Acknowledgement number always starts with 101010. In other words, the sequence number starts with 0, acknowledgement number starts with 1. Then when an acknowledgement number always is given, that acknowledgement number always defines the sequence number of the next frame to receive. Sequence number of the next frame to receive. So this example we'll see. There is a figure for that, shows how adding sequence number and acknowledgement numbers can prevent duplicates. The first frame is sent and acknowledged. You can see packet 0, sequence number starts with 0, packet 0. Acknowledgement always starts with 1. This means that next packet is with number 1, packet 1. Lost. Again packet 1 resent, acknowledgement 0. Next packet 0, acknowledgement 1 lost, packet 0 resent, acknowledgement 1. So is it clear? Then, so if a packet is lost, again it is resent after timeout. The third frame is sent and acknowledgement, but the frame is resent. Okay. Next, we'll discuss about FSMs with sequence and acknowledgement number. So it is possible to change the FSM, whatever we have just now discussed in this diagram. This FSM in this diagram, okay, to include the sequence and acknowledgement numbers, but that will not be discussed here. Okay. Next, we'll discuss about piggybacking. The two protocols what we discussed, simple and stop wait protocol, simple and stop wait protocol, they are designed for unidirectional communication. What does this mean is that data is flowing only in one direction, although the acknowledgement may travel in the other direction. So in the past, these protocols which were designed used to allow data to flow in both directions. But in order to make the communication more efficient, the data in one direction is piggybacked. So in order to make the communication more efficient, the data in one direction is piggybacked with the acknowledgement in the other direction. So, putting it in other words, when node A is sending data to node B, node A also acknowledges the data received from node B, because piggybacking makes communication at the data link layer more complicated. It is not a common practice. Okay, so this completes your module 1. In next lecture, I'll discuss further part. Okay, that's